All right. So let me switch over here very quick. All right, there we go. So let me here just recalling the continuity equation, which is what? We write on the two form, but the traditional form is this one over here, where you use the del operator. Okay? Or in initial notation, I mean, you can even put the comma t, but b comma I equal to 0. And this one, you can almost call it like, but the density comma t. No, but generally, the way I like to write this one is this form over here. Okay. Or this one over here. Because remember, this one, you need to take a derivative on the x, partial derivative on x, partial derivative on y, and partial derivative on z, no? Okay? All right, so we have three cases over here. I mean, three cases. We can do simplifications over here. So case one, let's say we're going to look at the steady state. So what those steady states means is that it's independent of time. So that means that the density does not change in time because it's constant. Okay? So this term over here would be going to 0. So you will have that rho. We have either, we're going to have the equation, this one here, but since the density is constant, you can write it as, yeah, or if you move the density to the other side, this is the classic one that you have. This is the classic form of the continuity equation for steady state. Or you could rewrite it as what? Or you can write it as v of I comma I equal to 0, but I will not like that notation over here. I will write what? I'd rather write partial of partial x sub I of v of I equal to 0. Okay, you can use either one. This is a classic one. I don't like this notation. I think the middle point would be this one over here. Okay, so actually here I did the two cases at once, because one I did the steady state condition, and then I said for density equal to constant. Okay, so this will be the case over here for steady state. So this is equation, so continuity equation. For steady state and constant density, okay? So you can have either form of the equation. So that's not the way I wanted to present it, but that's the way it's going to be. So what is the case for the incompressible? So incompressible flow is what? I think we kind of discussed it the other day. In this compressible flow means that the density is constant. So it's also applied to this equation. Okay, the way really I wanted to do is to the first one do the steady state, which means del of delta t will be equal to 0. Okay, and then this one, and then the second case was for rho equal to constant, but I mix them together. So again, the equation for incompressible would be the same thing, would be the same equation over here, which will imply that the density is constant. Okay, all right. All right, so now the following is worth pointing out because it permits the density. I'm trying to summarize my paragraph here. The density and the velocity vector to be separated. Okay, so basically the continuity equation, the way we know it is what? Is partial t. I'm just going to use the initial notation now, partial xi rho v sub I equal to 0. Okay? Now, if I take here for the second term, I can keep vi constant over here, and then I can take the partial derivative of partial xy for the density. Yeah? Okay? So this will be like the double derivative. The derivative of uv is u prime v plus uv prime, no? And now we can do here, we can keep the density constant, and we take the partial derivative of the velocities with respect to x, y, and z, x1, x2, x3. And this will be equal to 0. But now, what is this term over here? We did it the other day. If you remember, this is the material derivative. Remember, we look at the difference between the Lagrangian and the Eulerian reference frame. Like I was saying, like if you see a truck moving, okay, you can be watching it from outside, or you can be on top of the bed of the truck, no? Okay, so when this is 0, that means you are watching it. If you're on top of the bed of the truck, that means that you're gonna have velocities, okay? So this was really the definition of what we call the material derivative, which is d dt of the property density. So this is the material derivative. Okay, so that means that at the end, we can just rewrite this as what? D dt of rho plus rho partial v of I partial x of I. So if you want, this will be an alternate form of the continuity equation. Yeah, so alternate form. of continuity equation, which is in function of the material derivative. So once again, let's see what happens if we do the same assumption as before. If substance / material is incompressible, what does that mean? We said before, density constant, you're going to have d dt of rho that will be equal to 0, and you will have rho partial v sub I x sub I equal to 0, or as before, if we move the density to the other side, we have partial v sub I partial x sub I equal to 0, which is the same as before, as we have the same conclusion, no? All right. But again, what is nice about this notation compared to this one is that now we are able to remove the density from the inside the integral. I mean the derivative over here, no? And now we can separate into two different terms. So this one is constant. You have the derivatives of the density, derivatives of the velocity, as long as you use the material derivative. Okay. All right. So generally, you develop the continuity equation when you go to which class? You go to fluids, no? Okay. So we're going to continue with that. Okay, so we're going to look now at what is called the Newtonian fluids. Okay, so what is the definition of a Newtonian fluid? So a Newtonian fluid, and then I'll do a quick figure, it'll be easier. Is a viscous fluid for which the shear stress is linearly proportional to the rate of deformation. So basically, if you need to do a figure, this is the shear, this will be the rate of deformation. Just make that it will follow a linear line, no? So basically that the tau will be equal to some type of whatever this ratio will be. I mean, generally is mu, the point function of the velocity profile, but here will be for deformation. It will be linear. Okay? All right. So what we can do is that for a Newtonian fluid, the stress strain relation which is the constitutive equation is given by, all right, so we have the stress. This is kind of similar to Hooke's law, but this is for fluids, no? So it's equal to minus P delta Ij, that's the delta Kronecker, plus the shear stress will be tau Ij. Okay, so obviously this one is the easy one. This is the viscous shear stress, but let's call it here is a tensor. And now, what is the meaning of this one? This is the one that we did cover, but it might be a little bit more difficult. This is, remember, this is the one that was defining the static pressure. That we take P1 plus P2 plus P3, no? Because this is 1, 2, 3. Yeah? So basically, if the fluid is not moving, the first thing you do in fluid, you solve problems for this term be equal to 0, because there is no motion, there is no shear. Yeah, so maybe write that down. So for a fluid at rest, which means static, okay, statics, the tau Ij equal to 0, and the equation reduces to sigma Ij equal to minus P tau Ij. Okay, so this would be actually equal to what? Would be equal to minus P of 1 plus 1 plus 1 when I equal J, no? So this would be equal that sigma Ij equal to minus 3P. And we actually look at it a different way. P, the pressure would be equal to the stress divided by 3. I think that's when we did it the other day. So what does that mean physically? The negative sign and everything is that if you have, let's say, a sphere in the water, okay, the stress or the pressure would be in what direction? If it's all water around this, it would be a compressible stress, no? And following the sign convention, positive is tension, negative would be a compression, okay? And this value of the pressure here should be equivalent to what? Should be 1/3 of the stress. That's basically what it means. And this is what is called the hydrostatic. Okay. So that's the first case over here for a static, for a fluid at rest. So we're going to make it to the page 100. So for a fluid, for a moving fluid, so this instead of statics, this time will be like dynamics. Obviously, we need to keep both terms. Okay? Where, and this is I'll give you now those. I'll tell you where we got. I got this from. Where tau j here is a tensor that can be written out the form of k I j p q capital D indexes pq. Okay, over here, Kijpq is the tensor of viscosity coefficients. Okay, basically, guys, what do we see over here? This needs to be a linear relation, no? Okay, basically, this is the kind of equation, needs to be linear. So this will be the tensor viscous coefficient, and the dpq should be equal to what? The rate of deformation. Okay, that's what we say. So coefficients, this is 3, this is a tensor to the other 4, so this should be 81 coefficients. So that's why it's a lot easier to write the equation in that form than 81 lines, no? Or 81 columns. And dpq over here is the rate of deformation tensor okay, and dpq, I might derive it later on, another chapter, or I might not derive it, is equal to 1/2. You can write it actually in function of the deformation, or you can write it in function of the velocities. That's why I don't want to spend a full lecture. I'll just give it to you. Will be partial VP partial XQ plus partial VQ partial XP. Okay, this is like, I don't know if you can have full translation, or you can have a little bit of shear, and we can derive this expression. We might do it later on, but doesn't bring too much to the understanding. All right, so over here, what I want to say is that a lot of this stuff is given, I think I told you the other day, oops. Let me close this one. It doesn't go. All right. I told you the other day that if you will come in here, I did ask you to print a couple of pages. I don't know if you did. Where are there? 16, this one here. Okay, do you remember I asked you to print these pages? You see always be this coefficient isotropic tensor of rank 4. Okay, so some of the equations we're gonna see now actually come from these 2 or 3 pages that you have over here. Okay, you see here this is the isotropic material equals to CIJKL. It's basically the same thing, but they use a slightly different notation, and they have this form of equation. Okay, so look at those pages, but basically you have a little bit more detailed information over here, but I'm going to do it now here on the notes as well. All right, so this is the full equation for any type of material or substance, okay? But let's over here. Most fluids are isotropic. Which means what? The properties are the same. The rate of deformation will be the same on the X, Y, and Z. Okay? And along with the properties of the shear, so of tau ij and dpq, so most fluid are isotropic, and along with the properties of tau j and dpq, allows to reduce the 81 coefficients to 2 and the fourth order tensor Kijpq. Can be expressed in terms of two independent constants. Lambda and mu. Okay, these one are called the Lames constants. Remember we derived the Lames stresses the other day? Okay, so basically what we have is C attached pages, so C attached pages that I give you. Okay, without doing the derivation, you can write that K ij pq will be equal to delta ij delta pq plus mu delta ip delta jq plus delta iq delta jp. So basically, this is the equation now, coefficients. I rewrite this under the function of these two constants, the Lames constants plus this one over here. Okay? So basically, this K over here is this one over here. All right. So now, if I substitute into this equation, so substituting into, how do you want to call this one? Star, whatever, into star. What do we get? We get that the Newtonian equation, that the stress-strain relation becomes sigma ij of minus p delta ij, so this term remains unchanged, okay? Plus, hope I'm gonna have space, delta ij pq plus mu is the same thing, delta ip delta jq plus delta iq delta jp. And this should be times the dpq. Okay, so I just substituted. After some algebra, you get that sigma ij is equal to minus P, the static pressure. So this will be for static, plus delta ij dpp. You need to change the indexes, plus 2 mu dij. I mean, remember here that these indexes, PQ, IJ, VQ, you can substitute them, no? So you can say that if P equal I, then you have this one will be DI, no? Okay, so when you do all this stuff, you can simplify it to this type of equation. That's what happened. All right, so over here, what would be the two Lamé constants will define what? Basically, the same thing you had in solid mechanics. You have sigma equal to E epsilon. The Young modulus define the properties of the solid. In this case, the lambda and the mu are the Lamé constant, but will be related to properties of the fluid. Okay, so let me just write down where the two constants lambda and mu denote the viscous properties of the fluid. Okay, I'm gonna have to rewrite the equation. So, right, recalling the equation, I'm just gonna rewrite the same equation. You don't have to, you still have space on your page, but I have to because sigma ij equal to minus P delta ij plus lambda delta ij dpp. Okay. So for I equal J, okay, what are you gonna have? Delta Ij will be equal to what? 1 plus 1 plus 1 will be equal to 3. So the equation over here will become what? Sigma sigma I, can we say that? Will be equal to minus 3P plus 3 lambda dpp. No, if I use this one, sorry for that. If I use dpp here, it's going to be easier to change this one. Can I just put pp here? Otherwise, I should have put dii here. Okay, sorry for that. Plus 2 mu dpp. I do the same thing now. Okay, or this is the general form, sigma pp will be equal to minus 3p plus 3 lambda plus 2 mu dpp. I mean, I don't know if you have seen this form of equation before. I'm pretty sure you have, okay? If you have taken a little bit advanced fluids class, you should have seen this equation, okay? So if it is assumed that the mean normal stress, which is what? Is the sigma pp divided by 3, okay? Is independent of the rate of deformation. So I need to be careful here. dpp then what should happen? If we just say that if it's assumed that the mean normal stress, sigma pp, is independent of the rate of stress, that means that this term over here needs to be equal to 0. Okay, so this will mean that 3 lambda plus 2 mu is equal to 0, or generally this is given as lambda would be equal to minus 2/3 of mu. Okay, I mean, and now you can kind of see what's going to happen. We can go and substitute over here now to simplify further the equation. This is called here the name maybe will tell you something. Stokes condition. Maybe you know the Navier-Stokes equation. Okay, this is the same Stokes, no? I mean, this is kind of the derivation, part of the derivation to the Navier-Stokes equation. Okay, so now that we have this, we can substitute this one into this equation. Okay, so substituting into the stress strain relation, which basically is this one over here. So we have, maybe I should go to the next page. Okay, we have to write it. Sigma ij will be equal to minus p delta ij plus or minus, well, let's see here. I rewrite lambda or mu. Okay, actually I did a reverse, so okay, so will be, so lambda, okay, interesting. So minus, so I'm going to this equation and I write everything in function of mu instead of lambda. Okay, so will be then lambda, so minus 2/3 of mu delta ij dpp plus 2 mu dpp. Okay. Okay, so this is called obviously what? This is the stock equation. But what is something that is specific about this equation? Maybe you can write it down. I'm not going to write it down. Is that here, in order to define the properties of the fluid, the property of the fluid, you don't need anymore the two constants. You only need you need to know one of them. And actually, mu will be the viscosity. Okay, so you can define the equation of motion with just having one property of the fluid. You don't need mu. You don't need lambda and mu. You only need mu. Okay. So good. Yeah, you pay more attention than I was paying here. So basically that means that here you look at ij, this should be linear to the property ij. Okay. Yeah, I don't know why I put pp. Thank you so much. Yeah, this is now dpp, this is dij. But basically what's important over here is that now the equation, the constitutive equation is not in function of the two Lamé parameters, it's just in function of one of them. Okay? Okay, and now let us try to find a relation for dpp, which is the rate of deformation. That, what did we say before? Rate of deformation can be written in function of the velocity, so actually you can also write it down in function of the x, y, and z. Okay, you end up with the same thing. All right. So page 102, page 102. So for an incompressible fluid means density constant. What do we have for the continuity equation? The continuity equation is, let's just redo it, will be equal to what? Partial t plus, let's use, I'm just going to start using one notation, okay? Rho v sub I equal to 0. So if it's incompressible, this is constant, so this means this term over here is 0, okay? So we had over here, we just did it today, but rho partial xi vi will be equal to 0, or partial xi vi will be equal to 0, which was the same as we just did it earlier, no? We have this. Okay? Now we said that dpp, let me show this time that I pay attention to the indexes, which is the rate of deformation tensor. Okay, so if I write under dij, the way I wrote it before, let me change it. 1/2 is the same thing. I just want to use the notation that I have on the class notes. So I would not mix them anymore, plus partial vj partial xi. Okay, so if dpp equals 0, what does that imply? What is the meaning of these two sentences here? Is the velocity, change of the velocity with respect to each one of the directions. Okay, so this will imply that partial v sub I equal partial x sub j, partial v sub j, partial x sub, j x sub I would be equal to 0. So that means basically that the fluid is not moving. Yeah. Because basically, what do we say? That incompressible. That we say that. What is the consequence that the density is constant? Is that we mean that now the density or the properties of the density are not going to change in function of the location. Okay, so they're not going to change in function of the position. Yeah, does that make sense here? Okay, so the properties of the density are not going to change in function of the position. All right. And now we can write, so Stokes equation reduces to okay, so two cases here. Let's do this. Oh, I just do that once. Sigma ij would be equal, let's do first this case, minus P delta ij. So it would be the static case. Not moving. Non-viscous effects or non-viscous effects, which would be stress. So basically, this is the one we derived before static. Okay, but now, if dpp was equal to 0, what will be this equation here? Sigma ij will be equal to minus P delta ij. So this term over here goes to 0, okay, because dpp is equal to 0, plus 2 mu dij. And this would be the equation for which case? What is the condition we say dpp? I mean, we said this will be incompressible, no? What do we say if it's not? So this will be Stokes equation for incompressible fluid, which basically just means the dpp is equal to 0, what we just said.